Hello and welcome you all back for the review program. And today's session, the topic is going to be diagonalization by orthogonal transformation. So we are still with the first unit, as we have finished eigenvalue and eigenvectors and also the properties related problems. Also we have done the Cayley-Hamilton theorem and the application part of it. And today's topic is diagonalization by orthogonal transformation. How are we going to diagonalize a matrix by transformation called orthogonal transformation? So let us look into the steps and few key points where I have written here to in order to start with diagonalization by orthogonal transformation, we should know this certain basic steps, certain basic points which will lead us for the transformation. So let us discuss in detail about all the key points. Diagonalization by orthogonal transformation. So we should know what is this orthogonal transformation is, and diagonalization is nothing but getting the diagonal matrix of a square matrix A. Of a square matrix, we call that matrix as A. So here A transpose is equal to 1. This is a property where it says that A is an orthogonal matrix. So in order to say that A is an orthogonal matrix, so we have to prove like A transpose is equal to I, or this could also be given as A transpose I, both are equal. So we should know first what is orthogonal. So this is what orthogonal means. So in order to say a matrix is orthogonal, it should satisfy A transpose is equal to I. How to get normalized? So there are steps which we follow to find the diagonalization of a matrix, of a square matrix. So before we start with a few steps or the few points where we are discussing is one among that is normalized vector. How to get a normalized vector is, we know to find eigenvalue and eigenvector. Here, getting normalized vector is, let us take it as XR in general. We know the vector consists of a column, vector is a column matrix which consists of 1 cross 3. It means that it has 3 entries in it column wise. Here, to get the normalized vector is being done by each of its element, let us take that element as x1 divided by square root of sum of the squares of the all other elements, x1 square plus x2 square plus x3 square. Similarly, the next element is, if it is going to be x2, divided by root of sum of the squares, x1 square plus x2 square plus x3 square, and x3 divided by root of x1 square plus x2 square plus x3 square. This is how we are going to find the normalized vector. We know how to find the vector, and then this is the way to find the normalized vector. The third point is normalized model matrix. Here, model matrix is nothing but a matrix where it consists of all this normalized vectors and placed in columns. So if this is x1, normalized vector of x1, similarly we will get the normalized vector x2 and normalized vector x3. So normalized model matrix is nothing but getting the matrix of normalized vector placed in column wise. Placing the normalized vector Hello and welcome you all back for the Anna University EDU program, and here today's topic is diagonalization by orthogonal transformation. How are we going to diagonalize a square matrix to get diagonal matrix of that respective square matrix? So let us take any square matrix where we could find the diagonalized matrix of that square matrix through this topic or through this method. So let us start with the diagonalization by orthogonal transformation. So here we are going to get the diagonal matrix by a transformation called orthogonal transformation. We would have heard about this word orthogonal earlier in this unit 1 while doing eigenvalue and eigenvectors and properties related problems. Also we have done Cayley-Hamilton along with its uses and properties. So here, what do you mean by orthogonal transformation? It is nothing but getting A transpose is equal to I, proving A transpose. If we could prove A transpose is equal to I, it means that we can call A as orthogonal matrix. We can call a matrix A as orthogonal matrix. So here I have listed some 2-3 points where before we could start up with diagonalizing a matrix, we should know some basic steps. So in order to start with the diagonalization, let us know some basic steps before we get into the actual problem. So the topic is going to be diagonalization by orthogonal transformation. So let us know in detail about this topic. What is orthogonal? Orthogonal means it is A transpose is equal to I, or in other words you can also say that is equal to A transpose I. That is, it means that A transpose is equal to A inverse. A transpose is equal to A inverse. That is what we actually mean to say here. So yes, that is definition for orthogonal. We can call matrix A as orthogonal matrix. The next thing is normalized vector. We know how to get the eigenvalue and the corresponding vector for any square matrix. Here, what do you mean by normalized vector is we are going to get the normalized vector by, it's a way where we can find the normalized vector. If your capital X is x1, x2, x3, usually we will represent the column vector. We represent the vector as a column vector as x1, x2, x3 according to the order of the square matrix. Here, how to get the normalized form of it is x1. If this is the first entry of a column matrix, x1, if this is the first entry of the vector, x1 divided by root of sum of squares of all the elements of the column matrix, of all the elements of the vector, x1 square, x2 square plus x3 square, x2 divided by root of x1 square plus x2 square plus x3 square, x3 divided by root of x1 square plus x2 square plus x3 square. So this is a way to get the normalized vector. So we normalized the elements of the vector by getting the root of 1 by the respective element 1 by divided by root of square of, we are just square and we just add sum of the squares of the entries or all the elements of the vector. So in that way we can find normalized vector. What is normalized model matrix? Normalized model matrix is we are going to get the matrix, we are going to get a matrix where all the columns are normalized vector. All the columns are normalized vector. So this could be the first column. If this is x1, this would be the first column, and similarly we can get the second eigenvector and the corresponding normalized vector, and similarly third eigenvector and the corresponding normalized vector. So as we place this normalized vector column wise, that matrix formed, we call it as model matrix. or since we place all the normalized vector, we are going to call it as normalized model matrix. So it is going to be like a matrix which consists of all normalized vectors placed column wise. That is normalized model matrix. And the next point is, if A is a symmetric matrix, then normalized matrix M is orthogonal. It's a very important point where with this only we are going to get into the topic too. That is being related to the topic where to find diagonalization. They say that A is a symmetric matrix. Okay, A is a symmetric matrix, then normalized matrix N is orthogonal. So we have a normalized matrix. We are going to call that as M. We are going to call that as M. That N is orthogonal. Okay, the model matrix we represent by N. Normalized model matrix we represent by N. This normalized model matrix will represent with the symbol N. So that is what it's given here. So if A is a symmetric matrix, the normalized matrix N is orthogonal. What do you mean by this matrix is orthogonal? Then it means N transpose is equal to I. N transpose is equal to N inverse. It means that N transpose is equal to N inverse. That's why the definition just now we said, if a matrix to be orthogonal, then we say N transpose is equal to Ni. So here we say it is orthogonal matrix N is, normalized matrix N is orthogonal. So N transpose is equal to N inverse. Now, as we know, the similarity transformation definition is, if A is a matrix, then by similarity transformation, that is M inverse A M. Let me take a matrix called M, and this M inverse A M will also give you D. So this is what the similarity transformation means. So according to that, since N is orthogonal, you can replace this M by N. Here it is just a matrix, here it is N. Model matrix is nothing but placing the vectors alone column wise. Placing the vectors alone column wise, it is model matrix, that is M. Placing the normalized vector column wise is nothing but normalized vector, that is N. So by similarity transformation definition, if this is M inverse and here saying that N is orthogonal, this could be taken as N transpose A N, which is equal to D. So this transformation is called orthogonal transformation. So transforming A into D by means of the transformation N transpose A N is equal to D is known as orthogonal transformation. So we just blindly follow like what the similarity transformation means. What is M? It is a model matrix placing the eigenvectors column wise. So through that similarity transformation, knowing that a symmetric matrix and a normalized matrix N, which is orthogonal, we say that N transpose is equal to N inverse. So therefore N transpose A N, it is being replaced, like M inverse is replaced by N transpose and A is A and M is nothing but N, which is equal to D. So therefore this transformation. So we have taken a matrix A, we could find eigenvector for the matrix. Therefore normalized vector, normalized model vector, normalized model matrix, that is N, and the transpose of it, and which is being give you D, that is the diagonal matrix. So this kind of transformation we call it as orthogonal transformation. What is that? With this we are going to do problems. So let me take a problem. I have taken a square matrix. Now this question is like, this problem is about, we are going to get the diagonal matrix of this square matrix through orthogonal transformation. What is orthogonal transformation? Shall we quickly discuss the steps? Number 1. In order to get the normalized vector or a normalized model matrix, first we should know what is the eigenvalues and eigenvectors. So the first step, it could be finding eigenvalues. The second step is finding eigenvector corresponding to values. Finding eigenvector corresponding to eigenvalues. Corresponding to eigenvalues. And the third step is going to be finding normalized model matrix. Finding normalized model matrix, that is N. Then we can also find what is N transpose. You can just compute what is N transpose by knowing what is N. And finally, this diagonal matrix D you can find by matrix multiplication of N transpose A N. This is called orthogonal transformation. So these are the 5 steps where we are going to do it in order to get any square matrix to get a diagonal matrix. See here, what is the fourth point says? It's A is a symmetric matrix. So here symmetric matrix alone can be taken for orthogonal transformation. Only a symmetric matrix here. What is the third point again? We can recall that point. So A is a symmetric matrix, then normalized matrix N is orthogonal. If A is a symmetric matrix, then normalized matrix N is orthogonal. So always we check that whether it is a symmetric matrix or not, and then we can proceed with orthogonal transformation to get a diagonal matrix. So let us do this problem by working out all the 5 working rules, or called steps. What is the matrix is? 3, minus 1, 1, minus 1, 5, minus 1, minus 1, 1, 3. Let me check once again. Yeah. So what are the 5 steps? Finding the eigenvalue and eigenvector, finding normalized model matrix, and N transpose, finally computing D. So let us find eigenvalue. How do you find eigenvalue? Through characteristic equation. So characteristic equation takes the form, characteristic equation CH dot EQ stands for characteristic equation, takes the form lambda cube minus S1 lambda square plus S2 lambda minus S3 is equal to 0. Let us find what is S1 is. S1 is sum of the main diagonal elements. It is 3 plus 5 plus 3, which is equal to 11. How do you find S2? It is sum of the minor matrix of the main diagonal elements. So it is sum of the minor matrix. Let us get the minor matrix 3 minus 1 minus 1 5 plus the second leading diagonal element. The first minor matrix of the leading diagonal element 3 is 5 minus 1 1 3 plus. So this is the second leading diagonal element. The corresponding row and column, if you remove, this is minus 1 minus 1, this is minus 1, and this is plus 1. So sum of the minors of the main diagonal element. sum of the minors of the main diagonal element. So 3 is the diagonal, 3 is the first diagonal element. So as we remove the corresponding row and column, we get 5 minus 1 minus 1, 3. This is 3. 5 minus 1 minus 1, 3. And the next leading diagonal element is 5. So when you remove the corresponding row and column, you get 3, 1 minus 3, 1, 1, 3. And the last one is 3 minus 1 minus 1, 5. Let us calculate this. It is 15 minus 1, 15 minus 1, 14, less 9 minus 1, 8, less 15 minus 1, 14. So you get 28 less 8, 36. And how do you find S3? How do you find S3 is getting the determinant of the matrix A. So this is your matrix A, which is going to be diagonalized. Okay, let us find the determinant of this matrix. So it is 3 into 15 minus 1 minus 1. Already there is a minus, so it is plus. Removing corresponding row and column, you get minus 3 plus 1 plus 1 again into 1 minus 5. So it is 3 into 14 plus minus 2 minus 4, 12, 42 minus 6. So we get 36. So let us write the characteristic equation. Lambda cube minus 11 lambda square plus 36 lambda minus 36 is equal to 0. I just substitute all the values of S1, S2, S3 in the place. So this is 11, 36 and that is 36. So this is my characteristic equation. Let us find the values or roots of this equation. So let us try with the trial and error method. Let's try 1. So as we try 1, it is 1 minus 11 plus 36 minus 36. So it is minus 10, which is no way it is equal to 0. Let us try with 2. So as we try 2, it is 8 minus 11 into 2. It's 4. 11 into 4 plus 36 into 2 minus 36 is equal to 0. And here it is 8 minus 44 plus 72 minus 36. So we get, as we subtract this, we get 80 and it is 80 plus 80, so it is equal to 0. So lambda is equal to 2 is one of the root, one of the eigenvalue. So with this lambda is equal to 2, let us find the other roots by synthetic division. So the coefficient of lambda cube is 1. Coefficient of lambda square is minus 11. This is 36 and plus 36. So it's 0. Adding that it is 1. Multiplying we get 2. Adding we get minus 9. It is minus 18 plus 18. 36 is minus 18. So we get plus 18, actually it is minus 36, so we get 0. Now using synthetic division method, this cubic equation is reduced into a quadratic equation. In another way we have to find the two other roots, whereas we find only one root by trial and error method, and we used synthetic division to reduce that to a quadratic equation. Now the equation becomes lambda square minus 9 lambda plus 18 is equal to 0. What could be the other two roots? You can write minus 9 as 4, 8, 7. So 18, 4 and is minus 9 plus 18 is equal to 0. 3 could be the root, so it is minus 3. 6 3s are 12, minus 3 lambda minus 6 lambda plus minus 18 is equal to 0. So lambda minus 3 is one root, the other root is lambda minus 6 into lambda minus 2 equal to 0. Therefore, the eigen values are, what are the eigenvalues? 2, 3, 6. So these are the eigenvalues. We are going to find the corresponding eigenvector for it. How do you find the eigenvector? Let us find a minus lambda I of x is equal to 0. A is 3 minus lambda. So anyway, we are going to subtract only the diagonal entries because I is an identity matrix of a 3 cross 3. Since A is a 3 cross 3 matrix, I is also a 3 cross 3. So you will have only changes with the diagonal entries. So the other elements I am going to write as it is. It's minus 1, 5 minus lambda, minus 1, 1, minus 1. This is 3 minus lambda into capital X is x1, x2, x3, which is equal to 0, 0, 0. You can name this as 1. So let us find the eigenvector. We'll take this as case 1 when lambda is equal to 2 in first equation. So as we substitute 2 in first equation, 3 minus 2 you will get 1. 5 minus 2 you will get 3, 3 minus 2 you will get 2. So the reduced matrix is 3 minus 2, 1, minus 1, 1. Here it is minus 1. Here you get, it is 3 minus 2, 1. No? So here it is 3 minus 2. 5 minus 2 you get 3. 5 minus 2 you get 3. This is minus 1, minus 1, 1. This is minus 1, this is plus. This is plus. Minus 1, here it is, see, here it is 3 minus lambda, lambda is 2. So it is 1 into x1, x2, x3, which is equal to 0, 0, 0. Now we have, so when you look at this matrix, we could say that the first row and the third row are same. The first row and third row are two rows where which is they are same. It means that identical. So when two rows are identical, so when we frame that in terms of equation, again we'll have two identical equations. So whenever we have two identical equations or three identical equations, we'll consider that as one equation. So let us consider that as one row or one equation. So as we write it, we get x1 minus x2 plus x3 is equal to 0. Minus x1 plus 3x2 minus x3 is equal to 0. So these are the two rows. Let us do it by cross multiplication to find the eigenvector. So as we cross multiply, in order to cross rule multiplication, so by cross rule multiplication, let us collect the coefficients of x2, x1, x3 and again x2. x2 is minus 1, 3. This is going to be x3 and this is x1. x3 is 1 minus 1. x1 is 1 minus 1. x2 is minus 1, 3. So getting the determinant of this will give you x1, value of x1, that is 1 minus 3, it is 2. Minus 3, it is 2, which is equal to x2. Getting the determinant of this, it is minus 1 plus 1. Here it is 1 minus 3, it is going to be 2. Getting over this, it is minus 1 plus 1. It's going to be 0. x3 by getting the determinant of this. Getting the determinant of this circle, the last circle, it is 3 minus 1, it's 2. So x1 by 2 is equal to x2 by 0, x3 by 2. 3 minus, once again we'll check. It is 3 minus 2, 1, minus 1, 1, minus 1, 2, minus 1, 3, minus 1, minus 1, 3, minus 1, sorry, and 1 minus 1, 1. So these are the two rows which is identical, so I get x1 minus x2 plus x3 minus x1 plus 3x2 minus x3 equal to 0. Collecting the coefficient of x2, it is minus 1, 3, and x3 is 1 minus 1, x1 is 1 minus 1, x2 is minus 1, 3. So for getting the value of x1, it is minus 1 into plus 1, minus 1 into minus 1, plus 1, 1 minus 3, we get minus 2. We get minus 2. x2 is getting the determinant, this is minus 1, minus into minus, plus 1. x3 is equal to, getting the determinant of this, it is 3, minus into minus plus, already we have minus 1, it is 2. So this is minus 2. So this is going to be, now it is divisible by 2, so everywhere you can give out capital X1 is going to be minus 1, 0, 1. This is your first eigenvector. This is your first eigenvector. So let us find the second eigenvector. So case 2, when lambda is equal to 3, second and first equation. So what will be the matrix form? 3 minus 3, it is going to be 0, 1, it's minus 1, 1, minus 1, 5 minus 3, it is minus 5 minus 3 is 2, and here it is minus 1, 1, minus 1, 3 minus 3, it is 0. So we get into x1, x2, x3 is equal to 0, 0, 0. Okay. Now as we form this into an equation, we get none of the three rows, among the three rows none it is same, or none of the rows are identical. So each one is unique. So let us, either you can write with cross row multiplication, or by directly, since we have two variables, you can equate one and the other to get the values. As we write this in equation form, we get 0 x1 minus x2 plus x3 is equal to 0. So as we equate this itself, we could be able to get what is x2 and x3 is minus x2 is equal to minus x3. Negative sign gets cancelled. So x2 coefficient is, x3 coefficient is 1 and x2 coefficient is 1. And therefore, substitute x2 is equal to 1 and x3 is equal to 1 in the second equation, which you are going to form minus x1 plus 2x2 minus x3 is equal to 0. As we substitute this, we get just minus 1 plus 2 times of x2, we know x3, that is minus 1 equal to 0. So 2x2 is equal to 2x2 is equal to 2, so x2 is equal to 1. 2x2 is minus 2 is equal to 0. 2x2 is equal to 2. x2 is equal to 1. So capital x2 will be 1, 1, 1. Let us even check. So as we substitute here 1, 1, 1, it satisfies for any equation. So without being the actual cross row multiplication, I could able to get the second vector. So even if you wrote cross row multiplication, you will come out with the same vector. So I just wrote the second equation. This is this equation form. The first row is equation 0x1 minus x2 plus x3 equal to 0. So by equating, I am able to get x2, x3 values. Substitute x2, x3 values either in this row or this row. So maybe in here you will get one equation and here you will get another equation. Any of the equation if you substitute, you will get x3. So my x2 is 1, 1, 1. Let us calculate x3 now. Case 3. When lambda is equal to 6, that's a third root. So it is 3 minus lambda minus 3 minus 1, 1 minus 1, 5 minus lambda minus 1 minus 1, it's 1 minus 1. Here it is 3 minus lambda, that is 6, so minus 3. So here as we write this in equation form, it is x1, x2, x3 is equal to 0, 0, 0. Let us write it as equation minus 3x1 minus x2 plus x3 is equal to 0. x1 minus x1 minus x1 minus x1 minus x2 minus x3 is equal to 0. And the third one is 1 minus 1 minus 1, 1 minus 1 minus 3 is equal to 0. Here we have formed the equation. Now, looking at this three equation, none that you can say it is identical. So, by cross multiplication, let us find the third vector. So, in order to do cross multiplication, collect the coefficient of x2, x1, x3, again at x2. Coefficient of x2. From any two equations, you can do cross multiplication. So, let us consider these two. These two equations, I am going to consider it. So, it is minus 1, minus 1, x1, x3. This is x3, this is x1. This is x3 and this is x1. So, x3 coefficient is 1, minus 1. x1 is minus 3, minus 1. x2 is minus 1, minus 1. So, as we get the value of x1 by finding the determinant of this one, this 1 plus 1, x2 will be getting the determinant of this, it is minus 1 minus 3. Determinant of the last part, it is 3 minus 1. So we get x1 value is 2, x2 value is minus 4, and x3 value is 2. So capital x3 is 2 minus 4, 2. So throughout it is divisible by 2. You can also write it as 1 minus 2, 1. 1 minus 2, 1. So if you just substitute in any of the equation, it should be solvable. So 1 here, minus 2 will give you minus 3, minus 3. So it is plus 3 minus plus is going to be 0. So what the eigenvector we found is right. So this values you can substitute on any of the equation, whereas you can check whether it is equal to 0 or not. You can also even cross check the vectors whether it is correct or not. So x3 is 1 minus 2, 1. Now what is my next step is, I have to get normalized model matrix. Let us first try to write for this M. So M is, so what is our x1 is? What is our x1 is minus 1, 0, 1. Minus 1, 0, 1, 1, 1, 1. And x3 is 1 minus 2, 1. So this is what the model matrix is. You will just place the eigenvector column wise. Now let us find normalized eigenvector, normalized model matrix. So in order to get normalized model matrix, first we should get normalized vector. So normalized vector 1 is, how do you get elements of the matrix, each of the element of the matrix, so each of the element minus 1 divided by square root of sum of the squares of all its elements minus 1 whole square plus 0 square plus 1 square, and the next one is going to be 0 by anything is 0. So 0 by root of 1 square minus 1 square plus 0 square plus 1 square, and third one is 1 divided by root of minus 1 square plus 0 plus 1 square. So this is what normalized eigenvector, and this is how we get the vector. So what is your x1 normalized eigenvector will be minus 1 by root 2, 0, 1 by root 2. So similarly normalized vector x2 will be 1 divided by the root of 1 square plus 1 square plus 1 square, squaring the respective vectors and just adding it square root of the squares of the respective entries. So 1 divided by root of 1 square plus 1 square plus 1 square, 1 divided by root of 1 square plus 1 square plus 1 square, which is nothing but equal to 1 by root 3, 1 by root 3, 1 by root 3. Similarly, x3 is going to be 1 divided by, what is our x3? 1 minus 2, 1 root of 1 square plus minus 2 square plus 1 square, minus 2 divided by root of same 1 square plus minus 2 whole square plus 1 square, 1 divided by root of 1 square plus the same thing. So we get 1 by 1 plus 4 plus 1, so it is root 6 minus 2 by root 6, 1 by root 6. So placing all this normalized vector column wise in a matrix called normalized matrix N. So N is 1 by root, it's 2, right? 1 by root 2 minus 1 by root 2, 0, minus 1 by root 2, 0, 1 by root 2. Second normalized vector is 1 by root 3, 1 by root 3, 1 by root 3, and this is 1 by root 6 minus 3 by root 6, 1 by root 6. So let us find what is N transpose. N transpose will be minus 1 by root 2, transforming rows into columns and columns into rows, minus 1 by root 2, 0, 1 by root 2, 1 by root 3, 1 by root 3 is the second row, 1 by root 3, earlier it was second column and now it is second row, 1 by root 6 minus 2 by root 6, 1 by root 6. As we have found N transpose, and this is your N and this is your N transpose. How to get D? D is equal to N transpose A N. So let us first multiply these two, and the multiplied product or multiplied matrix we have to multiply with N. Therefore, we have to check whether we get the diagonal matrix. One application part of this problem, diagonalization by orthogonal transformation or by similarity transformation, is you will have the diagonal entries are nothing but the eigen values. What was eigen values? It was 2, 3, 6. So you will have the diagonal entries also as 2, 3, 6. That's the beauty of it. So let us find N transpose A. What is N transpose? It is minus 1 by root 2, 0, 1 by root 2, 1 by root 3, 1 by root 3, 1 by root 2, 1 by root 6, minus 2 by root 6, 1 by root 6, and it is being multiplied with A. Let us write what is the matrix A. 3, minus 1, 1, minus 1, 5, 1, minus 1. So it is 1, minus 1, 3. Let us do the matrix multiplication. You can also use calculator to find the matrix multiplication. So minus 1 by root 3 into 3, minus 1 by root 3. This is 1 by 2. This first row with the first column. So you get minus 3 by root 2. Okay. And this is 0 plus 1 by root 2. Then first row with the second column, minus and minus plus 1 by root 2 plus 0 minus 1 by root 2. And the first row with the third column, it is minus 1 by root 2, 0 plus 1 by 3 by root 2. First row is minus 1 by root 2, 0 plus 3 by root 2. This is minus 1. Minus 1. The second row with the first column, you get 3 by root 6 minus 1 by root. This is also 3. It's not 6, it is 3. 1 by root 3. It is root 3. 3 by root 3. First row with the first column. 3 by root 3 minus 1 by root 3 plus 1 by root 3. So the second row with the second column, minus 1 by root 3 plus 5 by root 3 minus 1 by root 3. And here the last one is 1 by root 3 minus 1 by root 3 plus 3 by root 3. And the last row is 3 by root 6. So the last row with all the 3 columns. So minus, it's a 3 by root 6. It's 3 by root 6 minus into minus plus 2 by root 6. 2 by root 6 plus 1 by root 6. So it is 3 by root 6 plus 2 by root 6 plus 1 by root 6. Yes. And here it is minus 1 by root 6 plus minus 10 by root 6. This row with this is 10 by root 6 minus 1 by root 6. And the last row is 1 by root 6 minus into minus plus 2 by root 6 plus 3 by root 6. So this is what the matrix is. Let us write what is a simplified form. We'll write on the next page. Minus 3 by 2 plus 1. So it is minus 2 by root 2 minus 2 by root 2. This is 0. This gets cancelled. This is 0. There you will get 2 by root 2. 0 minus 1 plus 1 gets cancelled, so you just get 3 by root 3. 3 by root 3. Here again it is 3 by root 3. Here again it is 3 by root 3. Last row. 3 plus 2, 5. Since the denominator is same, so 6 by root 3 minus 12 by root 6. 6 by root 6, 12 by root 6 plus 6 by root 6. 12 by root 6 and 6 by root 6. 6 by root 6. 6 by root 6 minus 12 by root 6. 6 by root 6. Let us check once again. Yeah, 6 by root 6 minus 12 plus 6 by root 6. Okay. Now what is this? It is actually n transpose A. Now this has to be multiplied with n. This has to be multiplied with n. What is our n? It is 1 by root minus 1 by root 2, 0, 1 by root 2, 1 by root 3, 1 by root 3, 1 by root 3. It is 1 by root 6 minus 2 by root 6, 1 by root 6. So as to multiply this, let us check what we get. So minus 2 into plus 2, it is 2, 2 by 2, 2 by 2 plus 0 plus again plus 2 by 2. Root 2 into root 2 is 2. Next entry is first row with the first column 0, first row with second column again, minus 6 by root 3 plus 0 plus 6 by root 3. This will be 0. And here it is minus 2 by root 2 into root 6. What do you get? Here it is first row with the second column, we get minus 2 by root 6. Yeah, it is minus 2 by root 3 plus 0 plus 2 by root 3. Yes, it's right. 2 by root 3. First row with the third column we get minus 2 by root 12. Root 2 into root 6, it is root 12 plus first row with the last, second row with the last column you get. I'm sorry. First row with the last column, it is minus 2 by root 6 plus 0 plus 2 by root 6 into root 2 is root 12. In the next line, let's draw this row with all these columns. So you get minus 3 by minus 3 by minus 3 by root 3 into root 2 root 6 plus 0 plus 3 by root 6. And here it is 3 by root 3 plus 3 by root 3 plus 3 by root 3 into root 3, everywhere it is 3. So denominator is 3. Root 3 into root 3. This is also 2. Plus 1. Here it is 3 divided by root 18 minus 6 divided by root 18 plus 3 divided by root 18. The last row is minus 6 divided by root 36. 6 into 6, 6 into 2, no? 6 into 2. Minus 6 in the numerator, minus 6 in the numerator, root 6 into root 2, it is root 12. 6 2 is 12. And plus 0 plus 6 by root 12. And here 6 by root 18, 6 by root 18 minus 12 by root 18, yes, 6 by root 18. And the last entry is, last element is 6 by 6, 6 by 6, minus into minus plus, 2's are 12, 2's are 24 by 6. Then it is again 6 by root 6 by 6 is 6. It's just 6. So what do we get here? Of 1 plus 1, it is 2. This is 0. This is 0. So let me write here. So 2 by 2, 1, 2 by 2, 1, it is 1. And here this gets cancelled, so it is 0. 2 by 2, 1 by 1, it's 2. 0. And this gets cancelled, it is 0. And here that minus 3 by root 6 plus 3 by root 6 gets cancelled, it is 0. And 1 plus 1 plus 1, it is 3. And here it is 0. Here again it is 0. Here again, see, minus 12 plus 6 plus 6, denominator is 0. And your 6 by 6 is 1, 24 by 6 is 4 plus 1, so you get 6. And this is what the diagonal matrix D is. So what was the eigenvalues are? It's 2, 3, 6. So the diagonal matrix has come out with the diagonal entries as same as the eigenvalues. So it was 2, 3, 6 as eigenvalues, and the diagonal entries also it is 2, 3, 6. So the diagonal matrix of the square matrix, what we have taken here is this. This is how we can find diagonal matrix of any square matrix, and this by orthogonal transformation you can do it provided the matrix is a symmetric matrix. So this is about with the problems in diagonalization. So here, since we are eigenvalues 2, 3, 6, we say the eigenvalues are not repeated. Eigenvalues are unique. We may have cases like when the eigenvalues are repeated. So as we solve many problems, maybe like we can get eigenvalues with repeated eigenvalues and not repeated eigenvalues and so on. The next topic here, continued by this diagonalization, is reduction of a very important 16-mark topic, reduction of quadratic form into canonical form. Reduction of quadratic form into canonical form. It is a continuation of the diagonalization of orthogonal transformation. So here we are going to first define about what is a quadratic form, what is a canonical form, and what is that, how it is being reduced, a quadratic form to canonical form. And this conversion is being done again by reduction of orthogonal transformation. What do we do in orthogonal transformation? We diagonalize a square matrix, we diagonalize a symmetric matrix by orthogonal transformation property. Here again, we are going to do that provided beginning, the matrix will begin in terms of quadratic form, and towards end, after the diagonalization is over, we'll convert that into another form called canonical form. So let us now define what is quadratic form and what is canonical form. What is quadratic form? Quadratic itself, it means like it is an equation of quadratic form. So let us define this. It is a homogeneous polynomial of degree. What should be the degree? What is this word quadratic is about? it talks about any equation with degree 2. So here also homogeneous polynomial of degree 2 in any number of variables we can take, in any number of variables. In any number of variables is called quadratic form. Is called quadratic form. So how to get this, or how do we write this is QF stands for quadratic form, or this Q represents quadratic form is equal to summation of Cij into Xi Xj. Xi Xj, where I varies from 1 to n and j varies from 1 to n and j varies from 1 to n. Okay, so here this is an example. We can give the canonical quadratic form as x1 square, any quadratic homogeneous polynomial of degree 2, homogeneous polynomial of degree 2 in any number of variables. So x1 square plus 2x1 y1 plus y1 square. It is a quadratic form in terms of two variables. X1 square degree is 2, here also degree is 2, here also degree is 2, and it is homogeneous too. And it is homogeneous to everywhere you can find of the same degree, and that is again 2. So this type we call it as quadratic form, or we define it as homogeneous polynomial of degree 2 in any number of variables. We can also give it in 3 or 4 variables. What is the canonical form is? A linear combination of squares of n variables. Linear combination of squares of n variables. So let us now get into detail about conversion of quadratic form into canonical form. So as we know, the quadratic form, see this could also be written as x transpose Ax. What is an x? It is a column vector. An x transpose is a transpose of column vector, and as we multiply this we get this a quadratic form Q. So let us take a quadratic form Q x transpose Ax. So we have a quadratic form which is homogeneous polynomial of degree 2n. Let us take it as 3 variables, since we everywhere go with the matrix of order 3, or you can also take with 2 variables. Let me take Q is equal to x transpose Ax. Let me see how it is being converted into C. Now what is x? It is a eigenvector. It's just a vector. It's just a vector. It's not an eigenvector. It's a column vector. X transpose is a transpose of a column vector. Now let us take a transformation. Let us take a transformation. X is equal to ny. Let us take a transformation. X is equal to ny. Then what do you know about this Q is x transpose n y whole transpose into A. What is y? It is again n y, which is equal to, now transpose of this will give you y transpose n transpose A into y n into A n y. We are not transforming this, we are just writing is n y. Now what is this part? N transpose A n is what? N transpose A n will give you D. So therefore your quadratic form Q is transformed to is being reduced to y transpose dy. Y will be a column vector in terms of entries like y1, y2, y3, etc. And D will be a diagonal matrix where you will have D1, 0, 0, 0, D2, 0, 0, 0, D3 into y1, y2, y3, etc. So as we multiply this, what do we get? We get D1 y1 square plus D2 y2 square plus D3 y3 square plus etc. So this is called canonical form. This is called canonical form. As we started with the quadratic form, under the transformation taking x is equal to ny, we could reduce that into canonical form d1. It's from a diagonal matrix. So as we multiply this vector with d and that with y, we get d1 y1 square. So here you will have only the square terms. So it is a linear combination where you will have only the square terms. So y1 square, y2 square, y3 square, and it will be of degree 2. So this form is called canonical form. In between what happens is q, it will be given like q x transpose x. And what are we doing here? We are taking a transformation ny, and out of which we get n transpose an. So how this q could be converted to canonical form is by n transpose an. How this n transpose an is defined as this n transpose an is nothing but orthogonal transformation. Just now we did diagonalization of a matrix by orthogonal transformation. So the quadratic form conversion to canonical form. So quadratic form can be converted to canonical form through orthogonal transformation. This is what the next topic of the unit is. Orthogonal transformation. Okay. You have a quadratic form like giving it as x transpose ax. Okay, that is summation of Cij into xi xj. From this how do you get the matrix? Is you can get the matrix from the quadratic form q x transpose ax is you can get the matrix from the quadratic form as by collecting the coefficient of x square here half into coefficient of x y. What will be the combination? So let us take this as x y z, and here it is x y z. So what combination of entry you can add it here? It is x y. So that's why I have written like half coefficient of x y. Here it is again half coefficient of x y. Here it is z. It is half coefficient of y square. I'm sorry. It's coefficient of, what is coefficient here? It is combination of x and z. So coefficient of x z. So next thing, here it will be the coefficient of half coefficient of x yx or xy, both they will be equal. Here the orthogonal transformation is possible only for a symmetric matrix. That is very important. So here it is half coefficient of xy and half coefficient of yx, both will be same. So here again we get coefficient of y square So diagonal entries as that, except the diagonal entries, you have to divide the other entries by 2. Half coefficient of the combination is y, is it? Half coefficient of combination of x, is it? Here it is coefficient of y, is it? Here it is coefficient of, this half coefficient of y, is it? And here it is coefficient of x, z square. It is y and z here, it is x, z here. So this has to be with this x, z. This is how we are going to get the matrix form from the quadratic form. So once this is being done, you will get the matrix. So this matrix will be diagonalized through orthogonal transformation by finding eigenvalue, vectors, and normalized model matrix, and then by finding out D is equal to n transpose A n. So once this is being diagonalized, then we will take the form, and the canonical form Q takes the form y transpose D y. That will be the last step. Now let us recall the working rule of steps. Q is equal to x transpose Ax. This will be converted into matrix. From this you will get what is matrix A is. This is how we have to get the matrix A by collecting coefficient of x square. Diagonal entries as such collected coefficients, and the rest of the entries it is going to be, you have to divide with half. The second step is eigenvalues. Third step is eigenvectors. And the fourth step is normalized. So we are adding one step before, we are adding 2 steps to the working rule of normalization. We are adding 2 steps to the working rule of diagonalization by orthogonal transformation. So one step as this one, previously one, and towards the beginning one, and then the last there is one more step, normalization, normalized model matrix. Transpose. The sixth step, quadratic form Q will be converted. As we find n transpose, this is nothing but D is equal to n transpose A. Seventh step, canonical form is equal to y transpose dy. These are the 6 working rules where we can use the 7 steps where we can find, where we can reduce a quadratic form into a canonical form. So this quadratic form, canonical form, where we can also add some more like finding nature through the quadratic form conversion, like this form. Y transpose dy will give you also what is the rank of the matrix, also the nature of the matrix, also how to find the index and signature of the quadratic form. Let us also define that. How to find the rank of matrices? Rank of the matrix is number of non-zero eigenvalues. This is the rank of the matrix, number of non-zero eigenvalues. Eigenvalues will be nothing but the diagonal entries of a diagonal matrix. So through diagonal matrix we can get the canonical form y transpose dy. So here you can get the rank of any matrix. You can get the rank of the matrix here by calculating the number of non-zero eigenvalues. Index. What do you mean by this index? We call this as index of the quadratic form. Index of the quadratic form. How do you get the index of the quadratic form is number of positive eigenvalues. Number of positive eigenvalues. Number of positive eigenvalues is nothing but your number to be given for index of the quadratic form. So how do you get the positive eigenvalue? By knowing the positive eigenvalue, number and negative eigenvalue, you can give the index. Or whereas this canonical form conversion, this step, this Y transpose D will give you, this will be a matrix where it consists of quadratic form will be where it consists of D1 x y1 d1 y1 square plus d2 y2 square plus d3 y3 square. So what is this d1 d2 d3? It is nothing but eigenvalue elements. So if d1 d2 d3 are positive, then the index will be 3. So it is calculating number of positive eigenvalues in the eigenvalues or the positive numbers, positive values in the canonical form, positive square terms in the canonical form. You can also give it as number of, you can very well also give it as number of positive square terms in the canonical form. Number of positive square terms in the canonical form. So we also define what is index, signature and rank. Rank also already we have defined. Signature is nothing but getting the difference between the number of positive eigenvalues and number of negative eigenvalues, or the difference between the number of positive square terms and number of negative square terms in the canonical form. This number of positive, again the signature of the quadratic form. Number of positive eigenvalues. Difference between number of positive eigenvalues and number of negative eigenvalues. And last is nature. Nature can be found in two ways. One is through eigenvalues, the other is through principal method. The other is through principal minus. Let us discuss in detail about two methods. How to get the nature of the quadratic form through eigenvalue is there are 5 different natures where if you can call the nature of the quadratic form stands for quadratic form. There are 5 different natures. So you can give the nature of the quadratic form as positive, definite. Nature of the quadratic form is positive, definite if all the eigenvalues are positive. If all the eigenvalues are positive. All the eigenvalues are positive. Okay. We can give a case like we can give the nature of the quadratic form as positive semi-definite. Positive semi-definite, whereas it has all eigenvalues positive plus one, at least one of the eigenvalue as 0. All eigenvalues positive with at least one eigenvalue as 0. Eigenvalue as 0. It means that two of the eigenvalue could be positive and one of the eigenvalue, if it is 0, then we call the nature of the quadratic form as positive semi-definite. And the third case is negative definite. What is negative definite is when you can get the negative definite of when you get the nature of the quadratic form as negative definite is when if all the eigenvalues are negative. If all the eigenvalues are negative. If all the eigenvalues are negative. And here negative semi-definite. Negative semi-definite will be again if all the eigenvalues are negative with at least one eigenvalue as 0. So this is being added here plus at least one eigenvalue as 0. The last case is indefinite. The nature of the quadratic form is indefinite if the eigenvalues does not comes under any of the above cases. Like if all the eigenvalues should positive, we call it as positive definite. With at least one 0 and the rest was positive, we call positive semi-definite. And if all the eigenvalues are negative, we call negative definite. And if one of the eigenvalue is 0 with the other two as negative, we call negative semi-definite. And where do we call indefinite is if any of a case where it does not fall under the above 4 cases, we call that nature of the quadratic form as indefinite. I will also discuss you about this principal minor method. So let us take a matrix as the other method to find the nature of the quadratic form. Let us take a matrix of the form. Let this be A11, A12, A13, A21, A22, A23, A31, A32, A33. Let us take a matrix A of this height. Now, define what is D. Okay, let us define what is D1. This D1 stands for element A11. Okay, getting the element of A11. So, positive element of A1. Getting the positive value of A11, that is modulus of A11. D2 is getting the determinant of the first minor matrix, that is A11, A12, A21, A22. And then is D3 is getting the determinant of A. Now this is the next method, is the other method where with all the values of this D1, D2, D3, we can also define the nature of the quadratic form. So as the quadratic form will be transformed into matrix, you will get a matrix of this type. Now with this D1, D2, D3, we can define the nature of the quadratic form. How that is possible is, again, the first type is if all di's are greater than 0. If all di's are greater than 0, then we can call the nature of the quadratic form as positive definite. Then we can call the nature of the quadratic form as positive definite. The second case, if all di's greater than 0, and the condition like at least one di is equal to 0. all di's means D1, D2, D3, D1, D2, D3. Since we have been talking about 3 cross 3 matrix everywhere, maximum we can find D1, D2, D3. In general case, you can take it up to order n. So if D1 greater than 0, then at least all di should be greater than 0 and at least one di equal to 0. So can any cases like what could be the nature of the quadratic form? Nature of the quadratic form will be positive semi-definite. Nature of the quadratic form will be positive semi-definite. Third case, if all di's, it means D1, D3, all odd suffixes D1, D3, D5, etc. Here there will be a possibility of finding only D1, D3. So if D1, D2, D3, or let us take D1, D3. D1, D3 are less than 0 and with D2 greater than 0, then if this possibility will gives the nature of the quadratic form as negative definite. Giving nature of the quadratic form as negative definite. And the fourth case is for di D1, 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 D3 less than 0 and D2 greater than 0 and at least one di is equal to 0. Among with this D1, D2, D3, if any of one di is equal to 0, we call it as negative semi-definite. Negative semi-definite. The last case is indefinite. So if any case which does not falls under the above four cases, like if it does not falls under semi-positive definite, positive semi-definite, negative definite, negative semi-definite, we call it as indefinite. So this is how we are going to get the nature of the quadratic form is. So let us recall. How do you find the nature of the quadratic form? Through eigenvalues is, if all the eigenvalues are positive, we call it as positive definite. Here, through principle minus, if all the di's are greater than 0, then it is positive semi-definite. There, if any of the all eigenvalues are positive, there if it is all eigenvalues are positive with at least one 0, and here all di's are greater than 0, all di's are greater than 0, at least one di 0, then we call positive semi-definite. Negative definite, all eigenvalues are negative. Here odd suffixes are less than 0, even suffixes are greater than 0, then we call negative definite. And negative semi-definite, if all the eigenvalues are negative with at least one of the eigenvalue as 0. Here odd suffixes are less than 0 and even suffixes are greater than 0 with at least one di equal to 0. And we can define the nature to be indefinite if that does not follow in any of the above four cases. So this is how we are going to find the nature of the quadratic form. So we have introduced what is quadratic form, we have defined what is quadratic form, canonical form, and we could also define how that is being reduced through orthogonal transformation, and we also defined what is rank, index, signature and nature in two ways. How do you get the rank is? Rank is nothing but number of non-zero eigenvalues or number of non-zero square terms in the canonical form will be the rank. And signature is difference between number of positive square terms or the number of negative square terms in the canonical form. How do you get the nature? It is just number of positive square terms or just number of positive eigenvalues. So this is about we are going to get the reduction of canonical form, quadratic form to canonical form. plus we could also find rank, index, nature, signature, etc. So let us do quadratic form conversion problems in the next session. There will be one problem with repeated roots and one problem with non-repeated roots. Let us try. And thank you for patiently listening.